Hello, this is episode 5 of New Uses for Old Circuits, Nonlinearity and Feedback. When I started this new series of videos, New Uses for Old Circuits, a few weeks ago, I had a general idea of what I wanted to do, topics I've long wanted to address and talk about, but I didn't have a very coherent idea for how it looked. I didn't have everything mapped out and organized. But now I can start to see that the series is starting to organize itself. As an artist, I often have a lot of ideas of things I want to do, and it can feel tempting to want to map them out and have a coherent idea, a coherent structure before you even attempt anything. But often I find that just having that kernel of an idea is enough, and that if you just go start making something and start engaging with that idea concretely, the idea will start to organize itself. A piece of music will begin to cohere around what's happening. And so it is with this series of videos. I can start to see something emerging, something cohering, at least into something coherent for the next few weeks. In the previous video, Studies in Linear and Nonlinear Systems, we looked into better understanding what linear and nonlinear systems are, their basic characteristics, their defining characteristics, and what mathematically sets them apart. That's to say that linear systems obey the laws of homogeneity and superposition, and you can see examples of that in the previous video. But that's to say that linear systems are scale invariant. They don't change what they do depending on the scale of the signal coming in. So in that video, we looked at what makes a system, a functional block in the synthesizer, a module, if you will, linear or nonlinear. In that video, we isolated the system itself, looked at the inputs of the system, the output of the system, and used that to figure out whether or not the system was operating in a linear or nonlinear way. And we saw that certain circuits have regions where they operate in a linear fashion and regions where they operate in a nonlinear fashion. In this video, we're going to take that theoretical understanding of what linear and nonlinear systems are and start to look at it through the lens of feedback. In this video, we're going to start to get a handle on what eventually we'll come to talk about as chaotic systems. In my video series on cybernetics from a few years ago, we started with a video called Basic Feedback. And in that video, we started with the most basic synth patch possible, running an oscillator through a filter and listening to the output. In that video, the feedback we patched was to take the output of the filter and go into the control input of one of the oscillators. In this video, let's simplify that even further. Let's take the output of the low-pass filter and just patch it directly back to the input of the filter. So this is just pure signal feedback. We're feeding the output of the filter into another signal input so that the signal is feeding back on itself, not so that we have an audio signal going to control something else in the chain. You're probably aware that this is what gives a filter resonance, usually by tapping the bandpass output instead of the low pass. You can already hear the filter become more resonant as we feed back the bandpass on the input as opposed to no feedback. So the feedback element of this circuit, is it linear or nonlinear? Well, in this case, the feedback system is literally just this patch cable. So the patch cable is maybe just attenuating the signal a little bit, but it's not doing anything to the signal itself. If we like, we can run the feedback from the bandpass through a simple mixer and then back out into the input to have control over the strength of the feedback. But it's a pretty subtle effect because this mixer is reducing the gain in our feedback loop by quite a bit. So we're not getting too much of a resonant bump even when we turn the mixer channel all the way up. But let's stop to think for a moment about what's going on in this feedback loop. We have some signal, here a sawtooth being filtered by the filter, and the output of that filter is going back to the input. All of the elements in this system are linear. Our signal has some harmonic profile, and the only thing that can happen using this linear feedback regime is we can strengthen or dampen the harmonics that are already present in the signal. Filter resonance simply amplifies the harmonic content of any sound at the setting of the cutoff frequency because of this linear feedback. At high resonance settings, you're raising the gain in this feedback loop to amplify the content in your sound at the specific cutoff frequency chosen by the filter over and over and over again, amplifying it more and more until you get some self-oscillation. We can play with the filter resonance itself to increase more of this resonant tone. And our feedback here, if we increase the feedback, you can see accentuates this resonant ringing on the scope, and as we change the cutoff frequency, it changes the frequency of that resonant behavior. And that by adjusting the amount of feedback, we get essentially another resonance control. Using an external mixer usually doesn't give us enough gain to get nice resonance, and so the filter itself, in its feedback path tied to the resonance control, has a lot more gain, but we'll get back to that in a little bit. But so far, everything here is operating in a linear way. We're only accentuating what's already there. Now, what happens if we replace this linear element with a nonlinear element? For this, let's use the middle section of the wave multipliers, and let's just use the low-pass output to feedback on itself, since that's what we're listening to. Well, that's pretty strange and certainly not giving us what we had before with linear feedback. Let's play around a bit and see what happens. So, what is going on here? By introducing a simple nonlinear function into this feedback loop, we all of a sudden get something completely different. In fact, I don't even know that we're hearing our original oscillator input to the filter anymore. Simply feeding the low-pass output back on itself through a nonlinearity has more or less obliterated the simple synthesizer patch we have set up here. We can maybe even just take out the oscillator altogether. So what's going on? Why is this? Why does this simple nonlinearity create such bizarre behavior? With the linear feedback we were looking at before, we were looking at a closed system. We had an oscillator going into a filter, and that filter output was being fed back to the input. But being a linear system, it obeys the law of homogeneity. All this feedback is doing is creating an iterative scaling process. It can boost or attenuate what's already there, but it can't create anything new. Think of using a basic delay pedal. Using a delay pedal, we can hear linear feedback in action. At low feedback settings, the delay feeds the output back into the input, but attenuates the signal every time, so that we get these nice decaying echoes. The sound is the same every time, it's just scaled in volume every time through the feedback loop. No new sounds are created. Of course, some delays have filters in the feedback loop, but we'll put that to the side for now. At some point, we increase the feedback control enough that the fed back signal is as strong as the input signal. So So the system starts to recycle the sound over and over again at more or less the same volume. We get in this kind of steady state. If we push the feedback control past this unity gain, this steady state, then the delays will get louder and louder with each time through the feedback loop. In a perfectly linear system, that'd be the end of the story. The system would just get louder and louder and louder and louder every time through the feedback loop. But the physical realities of the delay pedal mean that the device has headroom. It can't output a voltage more than the voltage that we supply it. So with extreme feedback settings, our signal quickly hits the headroom of the device and then has to stop. It can't grow anymore. And so nonlinearities begin to emerge. Maybe when the signal hits the rails of the device, you just get clipping. Or some kind of compression can kick in to squash the sound. Either way, if we let it keep going, we'll hear these nonlinear elements emerge. New sounds will start to emerge as these nonlinearities are kicking in. As we saw, a nonlinear system does not obey the law of homogeneity. That's to say that what the wavefolder here is doing depends on the signal input, and it behaves differently based on the strength of the signal coming in. So what happens when you have a feedback loop is you have the initial sound coming in and then out of the filter, going through this nonlinearity, which is processing that sound in some way. It goes back out into the filter. Now what we have coming out of the filter is a little different than what came in the first time. It's a little easier to understand this if we think in sort of digital terms, in terms of an iterative process rather than the continuous flow of electricity. We send a signal into our filter. That filter output comes in through the nonlinear processor, which processes it in some way and sends it back to the filter. Now, the next time through the feedback loop, what we have here is not what we had before. What we had before was the filtered sawtooth wave. What we have now is the filtered sawtooth wave plus the feedback of what came in. But the nonlinear element processes that signal differently than it processed the first one. What this nonlinearity does depends on the amplitude of the signal coming in. Our linear feedback system, using the simple mixer, processed the fed-back iteration exactly the same as it processed the original iteration. It simply scaled the feedback and sent it back in. But the nonlinear element is doing something different because the signal coming in this next time round the feedback loop is different from the initial signal. And so subsequent iterations through this feedback loop are going to create differences at every single point. What we have now is a cascade of nonlinear processes continuously reshaping and morphing the signal every time we go around this feedback loop. As we saw in the previous video, small changes in the input to a linear system don't have very big ramifications. It doesn't change what the system is doing. But in this nonlinear system, small changes can have very, very big impacts and start to cascade out of control. Now, we aren't in the iterative world of computer programs. We're in the continuous world of a constant flow of electricity. In the linear world, everything stays stable. Even if the linear feedback grows to infinity, the signal itself is just going to keep growing until, like we saw on the delay pedal, it reaches the headroom of the device, but nothing fundamentally is going to change. In this system, we have a nonlinear element that's listening to the system itself and reshaping how it processes the system. It's almost as if the system is now looking at itself and trying to shape or organize itself into something. This is at the heart of what I've called in this channel self-organizing sound. We can move these knobs all we want, but the system is going to decide what it sounds like. we can find regions of stability and regions of instability. This is no longer a system we really have control over. We can't consciously program this sound in the way we might do using an oscillator and a filter. We've simply created an ecosystem that organizes itself. But the system isn't random. There's no random generator in here. There's no white noise. There's no random nothing. And you can sometimes find regions of stability and get back to them. This is in fact a very simple chaotic system. We'll look at chaos a lot more deeply in future videos. But the basic idea of chaos is that very small changes in the initial conditions of a system propagate eventually into very, very different outcomes. In life, we're very used to chaotic systems because we live with chaos all the time. If I leave right now to try and catch a flight to Madrid, I may make the flight and get to Madrid on time. But if I leave in 5 minutes, maybe I miss the subway, and then another one doesn't come for a while. Maybe that turns into a 15, 20-minute delay, and then there's a long line of security, and maybe I miss my flight. If I leave right now or 5 minutes later, the result isn't necessarily me getting to Madrid 5 minutes later. That small change in the initial condition of this system, leaving 5 minutes later, can result in me not getting to Madrid until a day later. The nonlinearity is what makes this system exhibit chaos, because those small changes are dealt with differently by the nonlinear element every time. Now for fun, let's add the resonant EQ into this feedback loop as well. So we have a nonlinear element in the wave multiplier and a nonlinear element in the resonant EQ. Both of these systems can operate in a linear fashion at low settings. We saw that at low gain settings on this knob, the middle section of the wave multiplier doesn't yet hit the region where folding takes place. Same with the resonant EQ. With low feedback settings and gentle settings on the EQ bands, it operates in a very linear fashion. So if we throw our sawtooth wave back in here, we can try to play with the boundaries of linear and nonlinear feedback. You can hear the instabilities that the nonlinear element introduces. And down here, we can get this kind of linear region. What if instead we also introduce another nonlinear element, the triple wave shaper? Now, as I've been playing with these patches, I've also been playing with the Q control, the resonance control on the variable Q filter, which is creating a secondary feedback loop in the background. As we talked about previously, filters use linear feedback to create resonance. However, practically, that's not really the whole story. With linear feedback, if the feedback gain is too high, if it's above unity gain, then your signal will start to grow and grow and grow each time through the feedback loop. Filters such as the variable Q are specifically designed to rein in that runaway oscillation so that you have a nice self-oscillation when you turn the Q up, but it doesn't grow so high as to just hit the rails of the system. This is usually accomplished by a couple diodes or some kind of soft clipping mechanism, some kind of compression in the feedback loop so that linear feedback for resonance doesn't get out of control. But of course, when we're talking about compression, we're talking about a nonlinear system. So the resonance control of this filter is in fact linear for a certain region and nonlinear for other regions. It's just precisely calibrated to mostly give you this nice linear resonant feedback, but clip and compress the internal feedback loop. So if the feedback grows too high, you get a nice resonant self-oscillation rather than a self-oscillation that gets way too loud. To our ears, it operates as linear feedback if we're just using this resonance control on its own. But the inherent nonlinearities in the internal resonance circuit really start to emerge when you have other feedback going on around the system itself. Then the internal precise calibration that's used to control the gain of the self-oscillation kind of goes out of the question, and the nonlinearities of the resonance circuit really emerge. It's this use of feedback and nonlinearities that lie at the heart of the work of musicians such as David Tudor, whose hand-built electronics allowed him to explore these very same concepts. It also lies at the heart of techniques such as no-input mixing. Take an analog mixer and plug outputs into inputs, and you'll be able to take advantage of its preamps and their inherent saturation to create an ecosystem of nonlinear feedback sounds. In the next video, we'll dive deeper into all of this and start to build a basis of understanding for chaos theory, and start to see how the synthesizer can mimic and model things like weather patterns and population growth.